All right, all right. Astronomy Daily Live might be back. Might be back. I'm going to restart that and look for the live stream. There it is. Am I here? Aha. I think I am. I think I'm here. So, yeah. Yes, that seems to be working. See you over there. Okay, well, sorry for the little technical glitch. Happens. It happens. Time to time, it happens. Let's see if I can. Oh, I didn't mean to do. Well, yeah, I can do it that way. It's going to be there. Very cool. Okay. Let's see. So I'm going to. Well, I can keep that chat open. I'm going to pause that. Yay. Get my chat restarted here. This is a pretty slow machine. Yeah. Spam it, Uncle Bill. Thanks so much for everything that you do. Incredible. Incredible and amazing. All right, the last thing that I want to do, yeah, new stream even looks better. See that? It's a brand new look, looks better. Let me, I'm going to send this new link over to Bobby. Yeah, must have been a little funny business with all the switches in there. So yeah, well, come on in again, friends. Gather around. We had a little, disruption with the circle. We had a little, a little bit of excitement. Having to restart this, but we are getting there. And unfortunately, it'll just be maybe a little shorter live stream today. No biggie. 180726. Oh, 0726 part 2. Paste that in there, send that off to Bobby. Anybody else ever wants to be on the panel, send me an email, cosmiclettuce@gmail.com. And as soon as we go live, I get a little link and you can join the panel. And I think that'll be pretty interesting once that panel fills up a little bit. That's the one thing about this live stream that isn't particularly me, and that is talking this much. It's just not something that I normally do.
Hey,
Hey. I think we've got it this time. So I'm looking at the smartphone over there, and it's just my ugly mug over there. So I think we're good. You on now? Hey there, Andy. Nice to see you. Yeah, some technical things. Computer wanted to go off into La La Land, and so it did, and we sent we sent that to oblivion and scooped up some new fairy dust, and here it is. We made it. We made it. Yeah, that's kind of an interesting fail, Uncle Bill, that you had to go into some kind of parameter file and change it. That's pretty radical. Hey there, Daniel. Nice to see you also in the chat, all the way from Australia. It's just absolutely fantastic. I mean, it's so cool, right? That finally, we humans can hook up like this. I think this is, I mean, what we're doing here is really early and extremely primitive, right? I mean, um, I can say that just by looking at history, and being like, okay, telephones, right? You think of those and how they were right at the beginning, and that is similar, I think, to what we're going through now with all of this and um, the internet and all of that. Don't really know where it's going, but it's probably going to be pretty cool. Pretty cool. And as Carl Sagan says, right, if we don't destroy ourselves, I think we're going to have a great old time. So what I thought, we haven't looked at the sun in quite a while. We're told, right, don't look at the sun. Don't look at the sun. Well, here on Astronomy Daily Live, we look at the sun. Oh yeah, we stare right into it, right into it. But no worries, no worries. We have the technology.
12:30 in Melbourne.
12:30 in Melbourne. Yeah. Wow. Awesome. Yeah. It's definitely tomorrow. There. Now, UT time, right? It's 2:29 UTC on the 26th. So in England, it's early morning. Here, where I am, I'm in southeastern Arizona in the United States, where it's dark and quiet. It is 7 hours behind UTC. So for me, it's 7:29 p.m. So pretty convenient as far as I'm concerned. Not so convenient for.
I wonder if Florida's going to be like all DST all year round, forever and ever.
What's going to be that all year round?
Florida DST.
Oh, are they deciding to jump onto the bandwagon and not do daylight time anymore?
They're right. They're going to stay once they're on DST. They're going to stay on DST.
Yeah, and I think I've talked about this before. I don't really think it matters if we change times or anything like that. It's the only thing that really matters, right, is that everybody sort of agrees to it, or at least accepts it. So if um, people want to go on daylight time, it's all right. It's yeah. I'm not really against it. Um, Not really for it either. Um, yeah, maybe at some point in the past, it seemed like a useful thing, but it probably isn't. But as long as everybody knows, then it doesn't really matter all that much. So I've got some coffee here in the in the big thick mug. It's getting a little cold, actually, relatively speaking. And of course, I've got the hydrogen hydroxide tonight, HOH. I've got a nice full mug of it here. So cheers.
What is in hydrogen hydroxide?
What is hydrogen hydroxide?
Yeah.
It's HOH. Right there.
Like water?
A very, very similar, extremely similar to dihydrogen monoxide, H2O. Extremely similar. Yeah, no, this is just my extremely demented attempt at some humor. So, yeah. This chemical goes by many, many, many names. Water is one of them. So cheers. I just prefer confusing everybody because that's extremely entertaining. So yeah, what is DST? DST. What is that?
Daylight savings time.
Oh, okay. Okay. Oh, okay. All right. Yeah. I was trying to think if it was like, EST or um, MST, like that. But yeah. Okay. So yeah. As I said, as long as everybody's aware, it doesn't particularly matter. Switching around, um, uh, you know, I don't, I don't know. I don't necessarily think that that's incredibly confusing. If somebody is confused about that, then there's something else going on. So, I mean, if you're not able to, you know, figure out that, today is an hour later than it was yesterday, yeah, maybe something else is going on inside of that head.
Camille, during Atlantic Standard Time equals Eastern Daylight Time.
Hmm.
At my church, we get something called Mormon Standard Time. You're always late.
I don't think that that's only for Mormons either. All right, let's look at the sun. There are three spacecraft that I like to visit from time to time. All three of them are looking at the sun in slightly different ways. There's SDO, the Solar Dynamics Observatory. There's SOHO, which is I'm going to have to look that one up. And there's IRIS, and I'm gonna have to look that one up too. So let's and I think these are all basically the same size of telescopes. I mean, what it comes down to, right, is that they are telescopes that are looking at the sun, usually at wavelengths that we humans, and especially being down here on the ground, looking through the atmosphere, just don't have access to, like a lot of the ultraviolet wavelengths. We just can't see with our own eyes, and they don't transmit through the atmosphere either. So even if we could see in the ultraviolet, we wouldn't see anything at all. So I'm going to share my screen. And I think right before we get into this, I have to play doorman to one of the kitties here. So I'm going to share my screen, and we're going to go over to let's start at SDO, Solar Dynamics Observatory. And let's take a look, see what the sun is doing. Okay, I'll be right back in like 10 seconds.
7, 6, 5, 4, 3, 2, 1. Okay.
Okay, here we are. Whoop, I don't know
I
why.
think you're about 10 seconds late.
Am I about 10 seconds late?
Yeah.
Who's keeping track of that? I'm not. So this is something that I don't know if I've ever seen or not. Um, it's like a little graphic showing where SDO is. Huh. I have to investigate this a little bit more, see if we can oh, this is like real time.
Yeah,
Huh.
interesting. There.
I'm going to I want to check this out a little bit more. This is pretty interesting. This is uh this is just showing the orbit of the SDO. As you can see, it's a polar orbit. It's called the sun synchronous orbit, in that it's almost always looking at the sun, and that's why, I mean, it can be a polar orbit. So you can sort of see it down here in this graphic, right? Here's the terminator, right? So here is the night side, and here is the day side. Maybe the other way around. I don't know. This isn't looking exactly right. Doesn't look like it's up to date. Um, anyway, yeah, I'm gonna check this out a little bit more, and then maybe come back to this because this is kind of cool. And this looks new. I mean, I think we looked at this site maybe about a month ago or so, and I don't think that was here. I mean, I think I would have noticed that. So pretty interesting. But let's move on. Let's actually look at the sun. So data and then the sun now.
Are we going to be looking at stereo A and stereo B as well, or no?
Well, we could. No harm in that. Stereo A and stereo B are in pretty interesting positions, right? They're on. Uh, um, well, we'll have to actually look and see exactly where they are. But yeah, let's see. So SDO is a pretty um, high resolution camera that, as you can see, looks at the sun at different wavelengths. And you can see, I think you can see on the screen here that there's like a 193 and a 304, 171 and 211. That those numbers correspond to the wavelength in nanometers. So just add a zero if you want to convert that to angstroms. So all of these 193, 304, blah, 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 blah. This is all in the ultraviolet. Um, yeah, 335 is too. Seems to be some kind of weird patterning here. Not quite sure exactly what's going on there. They do have, um, yeah, they do have, let's see, well, 1600, that's still in the ultraviolet. So I think they do have, yeah, do have a visible, more or less a visible view as well. Actually, a few of them. And don't be fooled by these colors, right? This color is not the color of 193 nanometers. They just the solar astronomers got together and said, okay, look, we've got all these instruments up there, and they're looking at different wavelengths. What are we going to do about that? It's like, well, let's just color code them. So when you see the purple one, you know that it's 211 nanometers. And that's all that is, right? It's just being able to look at that and say, okay, that's that one. It's not actually what it looks like at that wavelength at all. In fact, we can't see these wavelengths, so what it looks like doesn't really make much sense. But what these are doing, of course, is they are looking at different wavelengths, which means they're essentially looking at different materials or different layers in the atmosphere of the sun. So you can see here, for instance, 211 is sort of the best one to see the coronal holes. And I'm going to pop up this one. So here's a coronal hole. It's like a hole in the atmosphere of the sun. So here we're seeing, deeper down into the sun than like here, right? This is kind of an interesting looking feature. Kind of cool looking. Might be associated with some sunspots, not quite sure. Pretty busy place though. We've got this material sort of spewing out here. If this was on the edge of the sun, we would see it, way, way, way extended out. That's pretty cool. Cool looking. But anyway, so yeah, there are usually coronal holes on the North Pole and the South Pole. Once in a while, you'll get a coronal hole in more towards the equatorial regions. And when that happens, we can pretty much guarantee that all the electrical activity on the Earth is going to change, because what these holes allow is a lot of material to sort of spew out of them. You're talking, protons, electrons, even like helium, nuclei, just all kinds of stuff, right? Just all kinds of garbage and stuff. And so when we get a coronal hole sort of, at the equator, that means that it's going to be directed towards us. And so it's sort of like a fire hose, right? Just shooting all this stuff out as it rotates, right? So it takes a few days for that material to reach Earth, which it does, and then I think Bobby, you would probably know this better than I. With increased activity in the atmosphere, does that make all the shortwave and VHF and UHF and all that? Does that make it better, or does it make it worse?
Now, when it comes to coronal holes, all it does is just cause a little bit of geomagnetic storming, but I don't think it's that little or no effect with shortwave.
Okay. Yeah, yeah, but it definitely, gets the atmosphere of the Earth, well, the ionosphere of the Earth, pretty excited.
But
Uh,
according to Tabitha Skull, I'm not sure you follow her on
yes.
YouTube.
Yep.
Oh, okay. She said that when it comes to geomagnetic storming, it may affect a heck of a lot when it comes to shortwave and GPS operating and stuff, but it's very good for road photographers.
Oh, of course. Yeah. Yeah. And, even better, for viewing the aurora is like a coronal mass ejection, where you actually have, some kind of explosive event, um, in the right place at the right time on the
I
sun.
I
That,
kind of like it better if you learn from either from Geos or Tabitha Skull and stuff.
yeah, cool. Cool, cool. Yeah. Hey, I should, I don't know, have I told you, the Aurora story yet? Maybe I'll save that, because yeah, I want to keep looking at the sun here. But yeah, I saw. Um, I don't remember when it was. I want to say maybe late '90s, early thousands or so. Um, Saw an aurora from almost just just north of the Mexican border here. So that was pretty interesting. But yeah, let's keep moving on here. Um, but yeah, basically what you're seeing is just different material, different stuff, um, and different layers. You can sort of see, you can sort of tell, sort of kind of tell that it's kind of hard to tell, I guess. Um, I don't know, this size and this size, yeah, that's a little bit hard to tell. That looks a little bit smaller than that. So yeah, we're just looking at different layers. And then what they've done here, right, is they've just taken three wavelengths and added them all up. And that makes for an interesting image. And with any kind of false color enhancement, that oftentimes allows you to see new kinds of relationships. And this is kind of cool. You're almost seeing, um, the different layers here, right? You've got this bright stuff that sort of seems to be down below this yellowish stuff, which seems to sort of be below sort of the purpley red stuff here. So pretty neat, that you can actually see different layers. Let's go over to that active region and sort of see what's going on there. Yeah. See, so a lot of the, tendrils here are sort of, yellow and orange, where a lot of the other material lower down, I guess, um, is this bluish or purplish. Yeah. Huh. The opposite of that. But yeah, false color imaging, that really, really looks a lot like pictures of Jupiter that I've seen. You know, isn't that isn't that, isn't that interesting, huh? Turbulence everywhere. So that's SDO. You can make movies with this thing. They have, I think they're MP4s. Let's see if just 48-hour video. Let's see if it actually comes up here. It'll probably, okay, wants me to play it. Looks like it's loading. Oh, there it goes. These are kind of neat to watch. You can load these and watch the sun. The sun basically makes one rotation about every 25 days. but that rotation period is different depending on if this area, um, like the equatorial regions or more north, things spin at a different rate. Pretty active place though, for sure. Looks like they were doing some messing around with the telescope too, a little bit, which is fine. We can deal with that. So that's 2 days of rotation, right? You can sort of see it just started, and then it goes around a little bit. And then they do that little thing at the end. So there's a little bit of a pop here. Watch. It's going to go boop. Pretty amazing. Let's go over to SOHO. And that is this Solar and Heliospheric Observatory. It basically looks at the sun in the same way. The only thing that's really different is they've got a couple of pretty cool instruments that instead of looking at the sun exactly, they are looking at the region around the sun. And they have a wide field view and a narrow field view. These are pretty because, well, it looks like it's loading. So what they've done is they've put this thing, it's called a coronagraph, in front of the sun itself, right? To block out that bright light. And then with software, right, they've sort of done this. So this, let's I think we can zoom in on this a little bit. Yeah. So this white circle in the middle would be the size of the sun, right? That's it. And then, you know, they don't want us to see all the weird optical effects that the coronagraph actually makes. So out to this radius, that data is pretty useless. So I think in software, you know, they blocked all that out. But what you're seeing beyond that is real stuff. It's real stuff being spewed out by the sun as we speak. And yeah, I mean, it's part of the corona. And in the background, you can actually see stars, and I think you can see down to maybe 4th or 5th magnitude. So, you know, pretty good. So with this too, you can make movies. I want GIF movies or MPEGs. I guess it doesn't particularly matter. Let's see. Oh, that's pretty. Oh, that's really small. Let's see if we can improve upon that. So this will take a little bit of time to load, but we'll see it eventually here. You'll see that the stars are moving from essentially left to right, and the sun stays in the middle, and you see all these other particles. Now, most of those are like cosmic rays, actual particles coming from the sun. Ooh, that was exciting. When you have some kind of event at the sun, you'll oftentimes see these, these little streaks and whatnot will increase by a huge amount. We'll let this completely load, and then it'll run a little faster and smoother. You'll be able to see the background stars moving. But But as you can see, you know, this is as of the 23rd, and it's already the 26th. So we've got quite a long movie here. I'm glad it's loading as fast as it is, given my bandwidth limitations. But the other thing that they use these for, not only, you know, to study the sort of the outer regions of the corona, is relatively often uh, they will find comets coming in, and I think they've definitely found like over 3,000 of them now. Most of them plunge right in, right? They go right in, and nothing comes out. So you know they either impact the sun itself, or you know probably way before they actually hit the sun, they vaporize, and that's going to happen regardless of what they're made of, right? I mean, if they're rock, if they're ice, they get too close to the sun, they're going to vaporize. So yeah, this is a great way to look for comets. There's actually a site, and probably not gonna be able to find it. Okay, so here we go. Here's the full movie loaded now, so you can sort of see that it's running a little faster, a little smoother, maybe. Looks like there's a cluster here of some sort. Don't quite know. I'm wanting to say that that's the beehive cluster, because aren't these 4 stars here? There's a 4th one coming in. Aren't these 4 stars? Isn't that Cancer? Cancer the crab? I thought that the beehive was more centered, though, in those boxes. Don't know for sure. Have to look that up. But yeah, there's a site that actually takes these images and looks at the differences between the images. So it takes this like image 1 and subtracts image 2 from image 1, and then it takes image 3 and subtracts image 2, 4 from 3, 5 from 4, on and on, like that. And that's when you can really see changes happening. Let's see if we can just really quickly, because if you haven't seen that before, that's a nice thing to see difference. Wonder if that will get me there. Difference images. Yeah, let's see if this. I don't know if this is gonna show things too well or not. Oh, and this is relatively old, but it doesn't really matter. But you can sort of see, especially when, you know, material is being spewed out, you can sort of see that's a pretty low res. Ooh, there we go. That was exciting. Another little blob going off to the left there. So you can still see, you know, these rays here are pretty much constantly changing, right? You sort of see them a little bit here, differences between 2 adjacent things. Here's one that kept changing. There's another little ejection there. I don't know why that thing's in the middle. It's kind of annoying. There we go. So you can see The circle here, of course, is that blocked area, you know, that we can't actually see. But everything else, so a pretty active place for sure. A little bit of noise, lots of cosmic ray type activity. That was a very slow ejection there. Did you see that one? Okay, I think it restarted. All right. Well, that wasn't the best one of those I've ever seen. Let's see if there's another one. Is this going to give me any joy? I don't think so. Looks like a broken link. Arrgh. Drat. I'm not really seeing it here. What's this one? We'll try one more. I don't think that's going to give me any joy either. Not much. Yeah, this is just showing some CMEs that happened in the past. Pretty cool though. All right, let's get out of there. Let's go back to here. So that's the wide field, and I think they call that LASCO C3. There's also a C2, which is I think the field of view is basically just that small part. That's what this whole thing is here. So we can look at those, and that's just view of the same thing. In a little bit more detail. Pretty amazing, though, of course. Interesting structures here. You know how they're all sort of aligned. You know, they go out in these almost like ribbons, right? A lot of people are starting to call these flux ropes, and that's, I suppose, pretty appropriate. A little bit of optical effect here on the edge. They're not quite blocking it all out. No problem though. We can deal with that. And let's see, can we make a movie out of this one? Whoop, not an MPEG. Oh, we can do an MPEG this time. Looks like it might be kind of small, or not at all. No, I don't think it's going to let me do that. Let's go over here. I find it interesting to see how these things change. You really don't notice them changing until these movies loop around. You know, they start at the beginning again, and then it's like, oh wow, that's really moved and changed, constantly changing. Lucky for us though, it's a pretty benign star, right? Most stars don't seem to be this benign, this calm, and you know, calm is a relative thing. This is a very, very active, extremely active place, just not active enough, which I guess I'm glad about. not quite sure what wavelengths these are taken in. I want to say it's probably ultra. I can't be sure. Wow, look how that's breaking up into a few. You've got these things at the North Pole shooting out, shooting straight out. Same here, and then along on the equator, you got all this other stuff. Pretty amazing. Changes quite a bit too. Looks like it's almost ready to start looping. Let's see if it will. Almost, I think. Not much time left. There it goes. Now you really see some action. You can see a couple of stars here. But watch when it loops back. So you really see a difference there. Here it goes again. You ready? Wow. So quite a change in just a couple of days. Watch this thing evolve. Look at that. Constantly changing. I like it. All right, let's go over to Iris really quick. Iris is probably my favorite website for their stuff. And Iris is the interface region imaging spectrograph. And the interface region is a region I'll have to remind myself what the formal definition of that is, but I think it's the interface region is a place sort of right between the chromosphere and the photosphere of the sun. So it's in a particular layer. And what they've got up there is they have an 8-inch telescope that has a spectrograph on it. So they can look at images and spectra simultaneously. And they do. I think one of the coolest things about this particular instrument is that they have all of their data readily available, and it's updated pretty quickly. Let's see. Let's look at the latest thing. Now, this latest data isn't quite available yet, but they're getting there, right? And this was quite a while ago, almost a day ago, right? So this data is almost a day old. Not too bad. Not quite available yet. So all this stuff we can't look at yet. Let's keep going. As you can see, there are 1,274 pages, right? Almost 20,000 observations. So let's go until we can find one that we can grab, and we can sort of look at the same time, see how they look at the limb of the sun sometimes, the edge. You see this black line there? Okay, that black line actually extends all the way down. That's the entry slit for the spectrograph. So that's an actual hole slit, I guess, in the mirror itself, and the light can go through that slit and be used in the spectrograph instead. And what that gets you is a spectrum along that line on the sun. So if you want to look at the spectrum here, it's available, right? If you look at the spectrum here, there's not going to be anything because you're not looking at the sun. If you're looking somewhere in between, yeah, there might be some stuff there. And this between here and, yeah, hard to tell how far out it extends. This is the interface region that they're talking about. But a lot of these, they're just looking at the surface. You know, they're not looking at the limb. They're looking at some kind of active region. It looks like here, you know, they're looking at a filament. Okay, and here we're getting some actual data, right? So you can actually see. So let's see if there's an interesting one here that we can gaze upon for a couple minutes. There's not really a lot of activity, so there's probably not a lot to see in terms of too much excitement, but let's just see. Oh, that might be interesting. Okay, so here are some examples of the spectra. So kind of hard to see, I know, but there's a dark line going right through there, right through there. Do you sort of see it? So what that's saying is that, okay, if you look here, what you're seeing here is the spectrum of that location. So this is now wavelength, right? This away. And this is actually spatial position, right? Wherever it is on the sun. So here, this is the spectrum of this region down here. So very, very cool. These are the magnesium lines. Or the magnesium lines. I can't really see. These are. Let's see if there's a. Oh, it's going to turn it into a movie. I don't want to do that. Let's look at these. To make an interesting, hopefully a moderately interesting movie. Pieces pop up. Okay, this is pretty short. Pretty short little movie. But you can see there's a lot of action there. I'd like to be able to make a little longer movie than that. 19 images, yeah. Let's try to find one that has a few more images than that. There's 80. Let's try that one, eh? Oh, we'll look at the same one here. So this is, I guess 2796 angstrom. So that's still in the ultraviolet. Can't quite see that with our own eyes, but be a few more images here, and you'll be able to see how this instrument sort of scans across the sun in order, you know, to obtain a lot of spectra, lots and lots of data. But maybe we'll be able to see these ounces a little more here and see what they're doing. Okay, there's not much there, but yeah, you sort of get the idea. So supposedly all this material is moving along magnetic fields. So a lot of material will just sit up and float, shoot up. They'll go up, they'll come down. Pretty amazing. Not the best example I've ever seen, but it's a pretty inactive sun at the moment, so we're not going to get a lot of prominences or anything like that. Let's see here. Anything else interesting? But what's really, really cool is if you want to do any kind of solar science, the actual, scientifically valid data is here. Ooh, so here's a 692 images. Let's see that one. Don't know if there's going to be anything interesting here. So yeah, magnesium, silicon, oxygen, and carbon. So very cool. Let's see if there's anything interesting here, and then we'll call it. We'll call it a live stream after this. Pretty amazing, you know. Trying to load. Looking at a very, very narrow field of view of the sun. Very complicated place. I don't know what's going on there. You can see this instrument is kind of scanning around a little bit. There's the slit. All the light that goes through that slit feeds the spectrograph, and that's what makes the spectra. Again, the magnesium lines and the silicon lines and the oxygen lines. And they can look at that in any location along this slit. So that makes for some. See if we can get a lot of this loaded. It's not even halfway. But here, we'll let that load. We'll come back. You know, one of the interesting things that you might want to do is this. I open up a new old one. It's going to kill my old one. Try that again here. I'm going to load this. You show your, see what else they got already. This is the X and Y position on the sun. So the center of the sun would be 0, 0, right? So the arc seconds in X and 152 arc seconds in Y. So as you can see, this is the limb of the sun, which is actually about 911 arc seconds from the center. See, 911 arc seconds is 15.2 arc minutes. Is about the radius of the sun, for sure. And you can see, that it's north of center, and that's why the Y is that size. So here's a field of view, also in arc seconds. What that means is just, you can sort of see that here, right? The instrument is actually moving, right? And it looks like, at least from this, that they're doing eight steps and then they loop back. And each step is 5.2 seconds long. Okay, raster, where? Okay, yeah, I'm still not quite sure what these field of views mean, but showing the number of images in this, and then these are links to the actual data, and it's FITS data. It's just regular old FITS. So if you can handle, you're good to go. How we doing down here? We're getting there. Getting there. I'll let this thing load. We'll watch it a couple of times, and then we'll get out of here. So this is just a measurement of the intensity of the entire field of view. And this, the reason why this is increasing, once we watch the movie, you'll probably understand that a little bit more. So I'm not going to give away the surprise quite yet. But we've looked at that a couple of times before as well. Now, is there anything else? Back to this guy. See if there's anything else he's mentioning. So this is sort of a larger region, and then where Iris is actually looking. All right, so it's looking there. It's the limb of the sun, the edge of the sun. A little bit of a active region there. Kind of interesting that they show tray flux along with this. Not quite sure why they would do that, but let's see. Let's go back. Almost loaded. Not much else to see here. Let's see how we're really close. Yeah, we've got 100 frames left. My bandwidth is pretty low here, so it takes a while for these kinds of things to load. Kind of interesting just to sit here and watch it load, but once it starts, we can really see a little bit of dynamics. See how active this place actually is. These little things, I think they call those spicules, and they think that they play a pretty major role in transferring energy from the photosphere and lower up into the corona. Okay, so here we go. We're going live now, so you can sort of see how the spicules just sort of shoot up, come back down. They just do that over and over and over again. It's kind of hard to see. Ah, there we go. Look at that. So do you see all that white stuff? When this loops back around, you'll see it again. But what that is, that's actual electrical interference that the cameras are picking up on, And the cause of that electrical interference, there it comes again. Look at that. That's major, major noise. Oh, here's some stuff falling in. Look at that. Nice. You know, tons and tons and tons of material here. But that noise is caused by when the spacecraft moves over and sort of through the South Atlantic anomaly. It's a region of space where the inner Van Allen belts sort of dip a little low, and it's South Atlantic anomaly is actually a pretty large region, but as the name implies, it's in the region of the South Atlantic, sort of leaning towards South America. Um, I think we actually know that it's moving. Oh, but every single time Iris flies through it, it gets a lot of noise. A lot of noise. So very, very cool. That's just a little piece of the sun there, doing its thing. And we're looking. We're watching it carefully. All right. Well, I think we're running a little bit long, so I think I'm going to get out of here for today. So my apologies for the technical difficulties. Happens here. We sort of take those things in stride. Yeah, I'm glad that the reboot worked. Whatever the computer was doing, to tie things up, just needs a reboot. I wish that we each had some kind of reboot button. It's like, oh, I'm getting just a little too weirded out. Where's my reset button? Right? Where's it? I want to reset. All right, I'm going to get out of here for today. So thanks for coming in again. I'll see you again tomorrow, 22 and a half hours from now. Now, tomorrow, if all goes well, if there's any chance at all of it being clear, I'm going to be out starting at 4:30 UTC, looking at Mars, looking at Saturn, because at 5 hours UTC, Mars is at opposition. So that's exactly on the opposite side of the sun. So that's a pretty monumental event. It happens every year. This one's a pretty close passage, though. So Mars is a little bit unusually big, unusually bright, and I think it'd be very, very cool for us to be looking at Mars as it passes through this opposition point. So that'll be happening. The live stream is still going to happen at 2 hours UTC, but then I'm going to pick it up outside again at 4:30, and see, the scope is back. There it is. Yay. So we'll be looking through that scope. I've got a modified webcam that I just slip onto the eyepiece thing, and we can look at Mars. So yes, because by definition, more or less, Mars is going to rise when the sun sets. So My sunset here is around what, 2:15 UTC, 2:30, something like that. So it will have been up for like 3 hours, 2.5, 3 hours. So that actually puts it at a perfect spot, perfect spot. So yeah, I think it'll be a good view as long as it's clear. And even if there's holes in the clouds, right? Even if we have to look through holes, I'll do it. If it's raining, I probably won't. But usually by that time, yeah, it's not going to be raining anymore. We'll just have to see. So yeah, I look forward to that. So for now, I'm going to get out of here. Peace, cheers, and all of that. And I will see you on the spin. See you later. Bye.